All right. Well, it is my pleasure to introduce Gert Cauwenberghs, who is a man of a jack of all trades. I had to look up his CV to figure out that he actually has a PhD in electrical engineering, because you could think of him as a neuroscientist or a computational scientist, and it's really a pleasure to have known him over the years here at UCSD. And without further ado, take it away, Gert.
Thanks, Eric, and everyone. It's good seeing you. So this presentation is also for Duygu, Kuzum, who couldn't be here today. In fact, we have this joint project, which is part of the of Tom's ONR Science of AI program. And let me dive right into it. So AI has been around for many decades and has resurged just recently. In fact, there was a big surge about 5 or 6 years ago when Google DeepMind basically won over a human, the human champion in the game of Go. And that was a revolutionary thing, because for a long time, this game of Go was one of the greatest challenges in AI, and it was never going to be solved in our lifetimes, we thought, but it was. And interestingly, if you go under the hood, you will find quite a bit of neuroscience taking place. In fact, the founders of DeepMind are actually neuroscientists in their previous lives. They were recording, they were doing MRI experiments, and they were definitely knowing how the brain works. And there's great inspiration of how DeepMind has structured this AlphaGo system for playing the game of Go, based on perception, visual perception almost, modeling cortex, and then also planning of actions based on reinforcement learning modeled after the dopamine system, basically the reward pathway in the basic ganglia. But also it's interesting to look at some of the power discrepancies that you have between the human champion, the defeated human champion, and then a machine that is about a factor 1,000 times more power. So it was an epic battle, but it was a very unfair battle. In fact, Google went deep in its pockets with resources that are unmatched by the human brain. So it's a bit unfair, and that really prompts us to look at ways in which the brain actually deals with information in a very efficient manner. And that has been the premise of neuromorphic engineering, which was started by Carver Mead about 30 years ago, in fact, almost to the day, 30 years ago, with his landmark 1990 proceedings of IEEE paper. So the premise here is to take inspiration not only from the function, but also from the structural organization and the physical foundations, the primitives of computing in the brain, in neural tissue, right? In the physics of computation, and more of that then into silicon systems that adhere to those principles in a very physical way. And that way, coupled also with learning adaptation, those systems are then able to not only function, but also being very resilient to variations in the process and the environment, and being extremely efficient, energy efficient for doing so, like their biological counterparts, right? And this is really a dialogue between neuroscience and engineers here. After all, what is neuroscience, or science in general, is about analysis, top-down approaches, basically abstracting the problem at hand of understanding how things work by going down to fundamentals. Whereas engineering is the complement, the opposite. It's the bottom-up synthesis approach of putting things back together and making them work right at large scale, taking advantage of abstract system-level representations at each level of scale, where you just have to worry about how the system then interfaces with its immediate interfaces at just adjacent scales in hierarchy, right? And so this beautiful hierarchy that you have here between different scales, which, by the way, Sejnowski came up with about also 30 years ago, right? In his book with Pat Churchland, right, on the computational brain. All right, so this stack is actually beautiful in the sense that at each level of the hierarchy, you have isomorphisms between the physics, the biophysics is what's happening in the nervous system, and then similar physics that happens in silicon with electrons and holes. In fact, Carver noticed very astutely that if you observe the opening and closing of ion channels and basically the conductance that you have of ions moving to those ion channels as a function of membrane potentials, you observe some of the same exponential dependence of those conductances and currents that you observe for electrons and holes moving through channels of MOS, metal oxide semiconductor transistors. Due to the same physics, almost Boltzmann physics. Basically, you have energy barriers. In this case, here with the voltage on the gate that controls then the transport due to basically the Boltzmann tail that you have of the energy distributions, right, and diffusion currents that you have here. So. And Carver realized that this exponential regime is actually a great regime to operate in because you have very large dynamic range of currents over about 4 or 5 orders of magnitude in current, while also have extreme low power because that range is actually, it's called subthreshold region of operation, where you have picoamp all the way from femtoamps to nanoamps of current. So you can get very efficient circuits for implementing your biological circuits. And so then literally neuromorphic engineers like Cauwenberghs have them build those circuits comprising those networks of here's photoreceptors, and then there's some the conductances modeled of a network, right, with all the way in the retina from horizontal cell, bipolar cells, American cells, etc., all the way then to the retinal ganglion cells that actually then communicate that information from the focal plane as spike events over the optic nerve to the rest of the brain. And it's amazing how much you can actually recover from that spiking, that event-based representation that is modeled here, right? You can actually reconstruct your scene. In fact, everything we see in the world is completely abstracted, right? From the spike trains that travel across your optic nerve, right? So neuromorphic engineers have then taken inspiration from that, building systems. Here's another example of event-driven image processing systems that rather than sending pixels, raw frames of pixels, we send just events when things actually happen on the focal plane. In this case here, a change in intensity that is detected here, right? This gives rise to extreme efficiencies in representations, right? So you can have systems that operate at milliwatts of power. And in fact, our latest work, we have actually brought it down to about 100 microwatt of power for an entire event-driven system. This is actually even better than the latest DVS systems. So now we're really in the microwatts of power for comparable to the efficiency of the human retina for transceiving that visual information to the rest of the brain. And then the natural question is, how do you deal with all this deluge of spike-driven, this event-driven spiking information from our senses? The brain has to make sense of it and then decide on control actions. And for that, we use that, again, inspiration from this the spike code that you have universally in the brain that can be efficiently represented with this, what is called this address event representation, in which only when a neuron spikes, there is an event that is communicated over a common shared bus, taking advantage of the massive digital multiplexing capability of VLSI to emulate the wiring in the brain in a virtual fashion, basically by having addresses stored in tables that then code the connectivity in your network, right? Which also allows for reconfigurable connectivity because you can change those connections on the fly by changing elements in your memory tables, right? So that was the premise of event-driven processing. And this has really enabled a revolution almost in systems, neuromorphic engineering, where we can put together multi-chip systems modeling different parts of what the brain is doing. And then the natural question is, what do you do with all? So how do those neuromorphic systems actually model the complexity of the real world, right? And so then you can look at task complexity versus machine complexity, right? The cost of computing, right, versus then what you're actually accomplishing with it, right? And for a long while, Moore's law has given us exponential advances in task complexity, in what can be done purely by doing nothing, just letting the silicon shrink. So I have now advances in the scaling of silicon fabrication technologies, giving us more transistors on the die. And this way we were able to do more complex things. But now as Moore's law is coming to an end, it's important to consider, right? So we can no longer go up and we can no longer inch up on the vertical axis of local complexity. So now we need to look at other means for extending our task complexities. And there, neuromorphic computing has been a great inspiration take inspiration from the brain. Both with deep learning, as I already mentioned, you can really think of deep learning. And then, by the way, deep learning started at UCSD about 30 years or 40 years ago. Terry was here, right? The entire PDB group was here, starting that field. And I would really say deep learning is neuromorphic engineering from an algorithmic perspective, but we also want to have neuromorphic engineering from a device's perspective to minimize then the energy per task, which can be decomposed as energy per operation times operations per task, right? Where this energy per operation can be minimized by device level optimizations, taking advantage of the physics of the medium. As Carver tells us, listen to the medium, what it tells us, right, to do. And we can get much greater efficient representations with processing in memory architectures as opposed to the traditional von Neumann compute architectures. And then we also minimize operations per task by this algorithmic advances of deep learning. So it's really now becoming a large community of researchers, all the way from engineering to science, all the way from EE nano engineering physics, right, of going after the scaling of the technology, right, being able to pack more neurons in small volumes at much lower energies per compute. Ideally, we'd like to get at the numbers that's comparable to the human brain if you want to get anywhere close to human intelligence. At the same time, a machine that has that many neurons and synapses doesn't mean it's intelligent. You still need to actually be able to train it and need to have massive amount of data to actually be able to get to that level of intelligence. And there it's about inspiration from neurobiology, computer science, and cognitive science, of abstracting from the complexity of the real world, just lower dynamic representations through deep learning. So here is a snapshot of the state of the art. Maybe it's not entirely up to date. Maybe I'm missing a few latest ones, but so those are then most recent chips that are doing reconfigurable neuromorphic computing. So reconfigurable means that they can in principle implement any network that you can define. And it's neuromorphic in the sense that they have more or less spike-based abstractions of neuroscience implemented in them. And they range from a few tens of thousands of neurons to about 1 million neurons in IBM True North here. But what perhaps, rather than looking for something that stands out between the digital approaches and the analog approaches, the real bottom line here is the as one metric that is that can be an apples to apples comparison across the board, is the energy efficiency in terms of joules per synaptic event. Neural events are important too, but it's really the synaptic events that comprise the bulk of all the computation that's taking place. And so, and typically the numbers here are about a few tens of picojoules per synaptic event. To put it in context, that's better than GPUs and FPGAs, but it's still far away from the energy efficiency of the human brain, which is about, if you have 10 watts of metabolic power, typically 10 to 15 synapses about active 1 to 10 hertz. So that gives you 10 to 16 synaptic operations per second with 10 watts. So that's about a femtojoule per synaptic operation. Right? So we're still about 10 or about 4 orders of magnitude away from that. And the other important consideration in all this is not just compute, but also connectivity. In fact, we all have white matter and gray matter, and the white matter is at least as important as the gray matter, getting the messages across the brain, right? And the event-based representation is great for doing so. But in order to really get across the brain efficiently, it's important to have this hierarchical representations, just the same way that the white matter is organized, right? In say, two hemispheres that are connected tightly. And then within each hemisphere, you have, again, this dyadic tree where you have these different sub-regions in the brain that connect, right? At the same time, you want to have the efficiency and the flexibility of the gray matter, which in principle, each neuron should be able to connect to any other neuron, right? So both flexibility of the gray matter and expandability of the white matter need to be taken care of. And I'll just say a few words here on hierarchical address event routing as a way for doing that efficiently, right? So the gray matter is represented here at the bottom of the hierarchy, and the white matter is basically this multi-scale connectivity network, right? Where at different levels of the hierarchy, you have this routing nodes that just pass messages. You can think of it as the white matter, the fiber bundles that pass the messages across the brain regions, right? And so what looks like a spaghetti network actually has structure if you look at it in different scales as a small world model. And then what you do, just have this relay neurons, or well, you can think of those are just axons actually, right, of your neurons that extend over long distances, right? Where basically you have this routing nodes that will then take local information when a neuron spikes and brings that through the network at different levels of scale. And only when that message descends down the hierarchy, you get an actual fan out. And the bulk of the fan out only happens at the root node in architecture, basically at the postsynaptic site. Right? So basically you port presynaptic information to the postsynaptic side, and then you can do local learning. So everything is basically ported. So then you have the gray matter, right, where you have the axons came all the way there, right? And then there you have your dendrites and then synapses, right, doing all the computation. So you can do local learning basically at the root node, at the leaf nodes of your architecture. So that's hierarchical address event routing. And you can implement this then efficiently, especially you partition the gray matter with this highly efficient silicon circuits that have analog continuous time dynamics, implementing, say, your synapses, your multiple compartments of your cells, the dendrites, and then your soma. And then, right, so you have synaptic information coming in addressed information coming in. And when a neuron fires, that neuron asserts the attention of the bus for an output event that is then communicated externally. So this system can be thought of as an integrated fire array transceiver. Spikes come in, spikes come out. And then on the outside, you have this architectures, digital architectures that route those spikes through those tables, these memory tables, for implementing the connectivity. And this is done in hierarchical fashion. So you have local tables for this local connectivity. And then you have this network of FPGAs and memory, memory for implementing then this network in the hierarchical fashion with multiple chips on board, multiple boards in a rack, multiple racks in a supercomputer center. And they can extend this across the network over the internet, right? Spikes over internet for, in principle, implementing any scale of your network, right? Very efficiently. Where at each node in the hierarchy, each node here has about a constant bandwidth because you have a small world network, right? But how do you make, so this is about 20 picojoules per spike event, limited mostly by having to off chip to fetch the memory. How do you make this now more efficient? Well, it's all about the memory. All the entire energy is consumed just by getting to the memory here, right? The slow memory that you have in typical DRAM, slow but fast memory in the DRAM, and then you have the fast and parallel processing that you have here in your silicon. So there's a mismatch that is to be taken care of by taking the memories and bringing them all the way to the compute, or vice versa. Take the compute inside the memory. And this is actually what can be done here. So rather than thinking of your arrays of memory elements, like in this latest emerging phase change memory or similar resistive RAM, RRAM technology, or this ST-RAM, or this MRAM, the magnetic RAM technologies. They're all, this latest technology are all conductance-based crossbar arrays, right? Where the memory is encoded as conductance of a crossbar element, typically with selecting a word line for activating this memory serially, right? Basically with an address that comes in. Well, replace the word line with just a presynaptic line that carries an action potential that activates that conductance between a reversal potential you can set here. And then on the bit line, you can just have your dendrite there, right? So right there, you have a biphysical synapse. You don't have to do anything. You can take the entire array, the entire technology, the same technology that memory designers have optimized in $1 billion industry, and directly leverage them purely by at the periphery of the array, right? By adding neuromorphic circuits that interface with those arrays, right? So you can get some great efficiencies for doing so. So with this crossbar array, so each memory element, right? Each crossbar element here, each junction does an instantaneous matrix vector multiply, right? An element in a matrix vector multiply, and you get fully parallel operation. So, right, you have a presynaptic action potential arriving along, say, all your vertical lines, and then you instantaneously accumulating all your currents along the membranes, along your vertical lines, right? Right, so in the preventive direction. They can even do spike time-independent plasticity, basically local learning, by basically projecting or connecting the rows and columns of your architecture with the appropriate timed pulses for activating them. Right, so you can take this crossbar arrays for synapses that are a very efficient implementation of this matrix vector multiply for basically all your synapses, and then couple them to silicon neurons that are underneath, right? Implementing then the neural dynamics, the membrane conductances, I mean and the actual excitability of the neurons, and also the learning can be implemented in those array of neurons. And then at the periphery, you can have now events coming in and events going out through this integrated fire array architecture that then coupled to other cores in the architecture for implementing this long-range connectivity. And this way now you have this white matter coupled with the gray matter here locally, right? And again, there's extreme efficiencies for doing so since everything is locally coupled here, right? And so here's one of these implementations that we recently did. This is work jointly with Philip Wong at Stanford of this concept where we have this RRAM, this resistive RAM array directly coupled with CMOS neurons that we designed, a 16 by 16 array of neurons coupled to a 256 by 256 array of crossbar RRAM elements for implementing connectivity at efficiencies that are orders of magnitude better than state-of-the-art. So now we're down to femtojoules, 13 femtojoules per centimeter operation. So only a factor of 13 away from the efficiency of the human brain in synaptic transmission. In addition, this architecture is reconfigurable in that you can revert the flow, the direction of the flow of information. So you can do backpropagation learning, or even better, you can do this going back and forth in inference and generative modeling, right? As in Boltzmann machines. And by the way, Boltzmann machines have also been invented by, this was by Hinton and Sejnowski about 30, 40 years ago. So we're all going in circles here. But those Boltzmann machines are great representations for deep learning, and generative models, generative modeling or generative learning has been undervalued in the latest rage of deep learning, and we'll get back to more generative learning, because now you can fill in the blanks. You can, if you fill in if you occlude part of the image, you can now reconstruct, not only recognize, but can also reconstruct your images, right? So for instance, here, this shows this in real time, where, well, almost in real time. This is recorded, but you can occlude a few pixels here in the 6, and then let the chip not only recognize that this is a 6, but also then recover the 6 as a template, right? At energy that are basically a factor about 1,000 times less than GPU or TPU or FPGA implementations. In our latest work, we're now extending those architectures to embedded with HIAER. So locally, we have the crossbar arrays for implementing connectivity and learning also jointly. And then at a larger scale, we have this HIAER, hierarchical address event trees for implementing then the connectivity between the cores, right? And so our latest work with Duygu has been to implement that cross this larger range connectivity, the HIAER network, actually also with crossbar elements of single. Those are a conductive bridge. Random access memories, basically silver lines that can be depleted or enhanced based on voltage with amazing resistance on-off ratios, basically going from kilo ohms to basically multiple tera ohms. So basically you can have a nice switch that you can turn on very reliably. And so this way we can implement this network. We can actually do this routing network implemented very efficiently with those devices at also great efficiencies and resilience, right? So endurance and retention is really state of the art, and so we can write either erase or program those connections within a milliseconds at energies which are a bit high in multiple nanojoules range, but still much better than basically what you, over a lifetime, what you would expect by basically having that switch there as an SRAM, as a memory storage element. And the density is also great. Right, so Duygu in her lab has then developed multiple versions. Those are two arrays here, 16 by 16 and 32 by 32 of those arrays. And then she also demonstrated applications of those technologies for really including some elements for vanadium oxide-based elements for even doing the compute as well. So with that, I will just stop here. I'd just like to acknowledge Onar, and I'd like to acknowledge Tom for greater support in this Science of AI program, and also many collaborators here. I just list here from my lab, but so Duygu also has a whole lab with other people working hard on all these different problems. And with that, I'll just, I know there are no questions now. The questions will be afterwards, right? So well, that's it.